Welcome to the second episode of Sentient, the podcast. Today we have with us here a very special guest. He is the current Einstein Award holder 2019. He is the Abhay Professor of Physics and the Director of the Institute for Gravitational Physics and Geometry at Pennsylvania State University. And he is one of the founders of the field in physics that is loop quantum gravity. We are immensely honored to have with us today Dr. Abhay Ashtekar. Welcome, sir.
Thank you.
Okay, sir. So, first of all, we would like to know a bit about your childhood in Maharashtra and how you first got into physics and experienced first-hand physics.
All right. So so as you say, I grew up in Maharashtra, and my father was in civil service in the state government, and so he was transferred quite often. And so I mean that was a custom that came down from the British tradition into the Indian administration system. And so we moved quite a lot. So in fact, I think by the time I finished, I had my education, undergraduate education, we had moved about 7 times. So 7 different places in Maharashtra, some very small, some slightly bigger. The bigger ones were Pune, and then finally the last 2 years of my BSc, I was in Bombay. So basically, I was always, not always, but I was often a new kid in the school because we moved, right? So a lot of students in the class were there forever. And I moved in and out. But in a way that, it might seem like, oh, what is a difficult thing? And in some ways it was difficult. But on the other hand, it prepared me to face new circumstances, right? I mean, like when I moved then in my adult career, many different countries, in some sense I was at ease. I kind of felt that, well, I mean, these people have been there, but I'm coming in, so I'll just join them at their level and then see what I can do. So I just mentioned because sometimes people feel that moving a lot is stressful, which is, but it also has a positive side. Then, I mean, the later years of my high school, I was in Kolhapur, which is a kind of a medium-sized city in southern Maharashtra. I guess somewhat well known for its sugar canes and for spicy food and such things. And then for the first 2 years of college, I went also to Kolhapur, Rajaram College, as it was called. I mean, frankly, my school was in fact St. Xavier School, but I have to confess that it was not a very good school, in the sense, at least when I was there, in the sense that it was not as well organized. In those days, for the higher secondary exam, the board exam or whatever it is called, we had to take 7 subjects, and for some accidental reasons or the other, we didn't have really good any teacher. In fact, for 4 of the subjects I was taking, right? I was taking 2 mathematics and 2 science options, and we didn't have really regular teachers for that because teachers left and they're not replaced and such. But again, there is a positive side to it all because it made me self-reliant, right? I mean, I just read things, and in some sense also gave me a lot of freedom. And so I think, again, that was something that was quite interesting and important for me, and turned out to be important later in life, because I was not kind of focused on just doing schoolwork. I was also reading. And in retrospect, from where I am in life now, I mean, I'm a bit surprised that I could get my hands on those books. I mean, for your generation, it is rather easy in the sense that you can just get to internet and find some topics and read. Your problem is the other way around in a way. Your problem is that you have too much information. I mean, you may not know which is good information, which is not good information. But our problem was really that, and of course, it's probably impossible for you to imagine life without cell phones. In fact, we didn't even have any phone at our house most of the time, except for 2 years, we didn't have any phone at all in our house. And it's probably impossible for you to imagine life without television, but we didn't have television at that time either. Okay, so this is good for you to sort of put yourself in a certain kind of a frame of reference from of but anyway, so I somehow managed to get my hands when I was in later years of high school, probably last 2 years of high school, um, some semi-popular science books. And again, I could do this in some ways because I had this freedom that we didn't have such regular, rigorous courses and such things. So I could read up whatever I wanted, and particularly I got interested in these books by kind of well-known Russian physicists who had settled in Boulder, Colorado, in the United States, by name George Gamow. And even today, you might find those books interesting, and they are outdated, of course, now. I mean, there was a book called 1, 2, 3 up to Infinity, which was giving paradoxes in mathematics, but also telling us about the early universe. And George Gamow, by the way, was one of the persons who worked quite a bit on nuclear reactions in the early universe. He is very famous for that. And then there was another book called 30 Years That Shook Physics, which had to do with basically 1900 to 1925 quantum mechanics. And so I got familiar with these things by the age of 15 or 16. I mean, I was reasonably familiar. But of course, it was at the qualitative level and not, in sort of detailed mathematical framework underlying cosmology or general relativity, but what the ideas were and so on and so forth. So that was kind of my, until my, what they call, what you used to call it those days, first year BSc. So that was, I think I finished when I was 17. So that was the age. And then at that time, I went to Bombay. And for my last 2 years of BSc, and at that time, kind of the good place to be was in the Institute of Science, which in the olden days was called the Royal Institute of Science, and then after the British left, it was just Institute of Science. And again, I have to confess that our professors were not that good. I mean, in the sense that they were not very active in research. Now, one thing I should backtrack just a minute, that in Kolhapur, when I was in my first 2 years of college, none of my professors there were actively involved in research. But they were very, very good mentors in physics, in mathematics, and even biology. They were very good mentors. They actually, for example, they let me borrow some books. They entertained my, my reading of these things on quantum mechanics and so on. I would ask questions, and they would actually answer those questions, and they encouraged me enormously. And I think that both in physics and mathematics. And so I think that to me was very, very important. By contrast, in Bombay, when I was in Bombay, it was really total sheer luck. I mean, I was extremely fortunate that just that year, two senior members at that time, senior members of the Tata Institute, started taking interest in undergraduates in Bombay. And so they started holding sessions in Tata Institute once a week for us. So we would go to the institute, in the institute bus basically, and we would be with them for 1 hour. And these were Professor Yashpal and especially Professor B.M. Udgaonkar. And they were just fantastic mentors for us because, we were sort of learning everything from books, and what we were learning was rather outdated. And we got to think more in modern terms, or more in terms that is needed to do actual active research, because this is the first time we're coming across people who were, familiar with the forefront research and were contributing to that. So one of the things we did there was really go through Feynman lectures in physics, which of course is now very, very old and so on. And we were doing all the problems. And then while doing a problem, I sort of at one stage I realized that there was it was total trivial, but mistake in the answers. Basically, I had done the solution, and I got the answer that was in the back of the book. They gave the answers for odd number of problems or something like that, and I got the correct answer. But then when I went and at night, I was while falling asleep, I sort of have some mathematics or physics problem in my mind, even today actually. And then I realized, no, I had made a mistake in that. And so next day when I got up and did it correctly, I had a different numerical factor overall. So then I presented this to TIFR people, and they said, yes, I was right. And so then uh, I wrote to, again, I was sort of a little bit brash. I wrote to Feynman, saying that, well, I think that, I did this problem this way and I got the answer in the book, but I think this is wrong, and so on. And then the correct answer, way of doing is this, I think, and so on. And Feynman kindly replied. And Feynman said that, yes, you are right, the book was wrong. But he also had a sentence which said that, basically said that you can rely yourself. In other words, he didn't want me to keep writing to him, pointing out some small mistakes here and there. And so that was quite encouraging. And basically, as a result of this letter from Feynman, and more importantly, the recommendation letters that people in TIFR wrote, I had also completely on my own, nobody suggested to me, done a little project, which was completely not very advanced at all. And sort of saying that, well, because I had read this Gamo's books about the early universe. And so I thought, well, supposing gravitational constant was not a constant, but it was actually time varying, then how would the scenario change? And I worked out equations. I know, I just had this junior BSc level mathematics. So it was not very sophisticated. I had no idea about differential geometry. Then, and I showed it to Professor Chitre, eminent astrophysicist at that time. And he was also, he was very kind. He commented on it in a very constructive way. But I think because of that, he also wrote a letter for me. And as a result of that, then so another thing, information in those days, right? So one did not know, for example, there's no obvious way to find out where to apply, right? Even within India, everything was by a little bit. If you happen to know somebody, you might know about, what is happening in IIT Kanpur or IIT Bombay, but otherwise one would not know what was happening. But then I went to what is called USIS. I don't know if it exists, United States Information Service in the consulate. And there they had little brochures about various universities. And I found a brochure saying University of Texas had this, it was correct actually. At that time, the biggest general relativity group, and it was a very distinguished group. So I wrote to I applied there. Unfortunately, I got in. And so I was in Texas for a couple of years. I started my research there. And then my advisor, Bob Garrosh, he moved to Chicago, and I went to Chicago with him. But I should say that in terms of relativity, general relativity, the Texas group at that time was much more kind of strong. It was the premier group in the world. And I was very happy to be there. Really leading people. They were, and it was also big because general relativity at that time was a very small field, very, very small field. So for that small field, it was really a big group. About 8 faculty members, and all of them totally leaders in science. I know that you are beginning people, so you will not recognize the name, but anybody who sort of, not even general relativity, but who is actually interested in particles and fields and cosmology would recognize them as leaders. So I was very fortunate that, I had this ladder through which I entered the research atmosphere. If you want any clarifications or, ask them questions about this part, please feel free, or we can go to the next part, whichever way you want.
Sure,
One thing I would like to, yeah. When you were a student, a master's student, a bachelor student, quantum mechanics and general relativity, they were still, relatively new fields, and people had a very hard time grasping these topics because they were a bit unconventional. So how were you taught these topics by your professors?
Yeah. Really, the correct way of thinking about general relativity and quantum mechanics had not filtered through. So when I was I did not do a master's. I went to the US immediately after my BSc. And so at that time, we had really not very much of a quantum mechanics, and not even iota of general relativity, not even semi-popular level of general relativity. But I sort of, there are good books, of course, much better bookstores in Bombay than in Kolhapur. And I used to visit them. Libraries were quite good. So I'd done some reading and I had some, vague idea about these things. But what we were taught in those days was really what is called as old quantum mechanics. No general relativity, but old quantum mechanics, like Bohr atom and something like, not really understanding kind of the operators and Hilbert spaces and the way that the real quantum mechanics is all about. It was really an older part of quantum mechanics. So, so because I went to Austin, Texas, just after my BSc, and as you rightly asked me about my background, I really didn't have much, right? I was very behind in the rest of the classes. So the first 2 years, I had to work extremely, extremely hard. It was a big challenge, but challenge does mean difficult, but also has a very positive part because you are motivated. There's so many things to learn. So you put all your energy. And those were 2 years of my life that I worked very, very hard, among the hardest that I worked at ever. Among, not the hardest, but among them. And so I had to pick it up. But then once I was in Austin, I did way because the professors there taught us the modern way of looking at quantum mechanics. And I did learn general relativity, not the most optimal way, but almost the most optimal way. Again, I was fortunate because the person I started working with, his famous relativist, Professor Robert Garrosh, he had just finished his postdoc with Penrose, Roger Penrose, and they were really doing state-of-the-art modern differential geometry, thinking about things in those using modern tools and modern physics ideas. And so therefore, I could learn those things very well with them. So really, I sort of was, sometimes you're taught in a bad way. And I find it with my own students here, that the students who don't know very much, when I teach them a course, I always make a point to make sure that people follow, have my office hours, ask people to come there and so on. People who are learning it for the first time get it right very, it's often much faster than people who have learned it before in a wrong way. Because once you think about it, get used to thinking in some outdated way of thinking, you kind of feel that I know the subject, but in some ways you don't know the subject. And then erasing something that you know and replacing it with what is a correct thing is often very difficult. So I was very fortunate to conclude that in Austin, I just really first-rate exposure to both quantum mechanics and general relativity by really extremely good people.
Okay, so I guess we should start with physics then. Okay, so my question for a start was that gravity is one of the most fundamental forces of nature. So why does it not seem to harmonize with the other three fundamental forces? What's like the problem with gravity?
So gravity is, first of all, you experience it every day, right? You drop things. The other forces, we experience them only indirectly, in the sense that we see light, and that is electricity and magnetism. But on the other hand, or you might get a shock from touching a wrong circuit. That is first-hand experience of electricity and magnetism, if you like. But we don't experience them all the time. Whereas gravity, we are bound on Earth, or this. So it is the oldest kind of studied force. There's no question about it. But the point is that gravity is universal in this following sense. Gravitational pull or gravitational force acts exactly the same way on all bodies. That's not true with electromagnetic forces, for example, because if you have electric charge of one sign, then in a given electric field, the particle would move one way, and if the electric charge is on the opposite sign, then the particle move in the other way. And similarly with magnetic field, it will depend on the velocity of the particle and so on and so forth, the trajectory. Whereas in gravity, all the bodies, there's universality. All bodies fall at the same rate. All bodies experience the same gravitational force. So there is a universality. And the second thing is that gravitational force is macroscopic, like electromagnetic force, in the sense that It's not just subatomic particles. It is a long-range force. It's the gravitational force is between Earth and the sun is what makes the Earth go around. So it's a long-range force. I mean, there are atoms on Earth and there is atoms on the sun, or elementary particles, nuclei on the sun and the nuclei here. But the force between them is completely, totally negligible, because the force drops off so fast that even at a centimeter size scale, the force is completely negligible here. So the other forces, the weak and the strong forces, are short-range forces, whereas gravity and electromagnetism are long-range forces. And gravity is always attractive, whereas and therefore universal, whereas electromagnetism is not universal. So universality and the long-range character of the force. So it's because of this, the following thing happens. You can never shield gravity. I mean, in the labs, there are labs, for example, which are shielded with respect to electromagnetic fields. So no external electromagnetic fields can enter the lab. You can never do that with gravity, because again, gravity is really, the gravitational charge, if you like, is only of one sign, not of two signs. And therefore, there's no place in the universe where gravity is absent. There's a lot of places in the universe where there's no electromagnetic field, force, or there's no strong or the weak forces, because you just don't have those particles, if you like. But in gravity, you just cannot escape gravity at all. So therefore, the beautiful thing that Einstein realized was really that as a result, gravity can be absorbed in the very geometry of space and time. So other forces they're really forces, but in general relativity, gravitational force literally disappears. Gravity is just a manifestation of the curved nature of geometry of space and time. So if I got sort of a massive object, according to general relativity, what it does is to bend space-time around it. So geometry of space-time is not like a stage on which things happen. You see, in Newtonian physics, space and time are just inert. It is forever. It's just sitting there, and things move. Like planets move, you and I move, the chairs, if we can move them, and so on and so forth. So we're all actors, whereas space-time in Newtonian physics is like a stage on which things happen. But in general relativity, I like to say that the stage joins a troupe of actors. There is no spectators. There is no stage. Everything is acting with everything else. It's a really very modern idea. And this idea actually people have taken in the literature also sometimes, using general relativity as inspiration. People have written there is a book in which the book itself is a character in the book. So it's a very interesting idea if you think about it. So it's the same thing here, but here it's literally true that there is no spectator. Space-time, things happen in space-time, but space-time can be acted upon. A massive body will bend space-time. And then other objects will move in that bend geometry. So sort of a visual impression, since I don't have diagrams to show you, is that you just can take a surface of an orange or an apple, if you like, and you can see an ant moving on it. So as far as the ant is concerned, the ant thinks that it's going as straight as it can, right? It's just going in a straight line. But we see it and we see that it's actually in a bent. I mean, for us, it looks like it's a bent path, because we think it from a perspective of a flat space. We don't think in terms of intrinsic geometry of the surface up here. And therefore, to us, it looks like it is bent. Same thing is true in relativity, but on a more profound level, because now we're talking about not two-dimensional surface, but four-dimensional space-time. And that space-time is bent. And literally, like the Earth, that is, for example, by sun. Sun has bent this space-time because of its large mass. And Earth, being like an ant, like a test particle, is trying to move. And literally, in this bent space-time, the Earth, which is an ant here, is moving in this by the analog of the straight line, the shortest possible path. In space-time, it turns out to be the longest possible path, but let's not get into technical details. But it's really trying to move along space-time. It's called geodesics. But from the Newtonian perspective, just like we see the ant moving on in a curved way, not a straight line. So from a Newtonian perspective, that it looks like the Earth is actually undergoing a bent orbit. But from perspective of bent space-time, Earth is following the simplest path. Now, this is a long introduction to your question, but gravity is spatial because it's absorbed in the very geometry of space-time. Whereas other forces, they are exerted between matter fields and so on, like particles, charged particles, you can have particles of so-called internal charge in quantum chromodynamics and so on and so forth. But those forces are they cannot be absorbed in the very geometry of space-time. Now, because the gravity is absorbed in the very geometry of space-time and others are not, that distinguishes the gravity from these other forces of nature. And in particular, we might go into that a little bit later, but when it comes to quantum mechanics, that is why the idea of unification of forces with quantum mechanics has not been so difficult with the other forces, but it's very difficult with gravity, because gravity is not literally a force. Gravity is literally, the best description we have today, a general relativity of Einstein, gravity is a manifestation of curved space-time geometry. And that is why it is on a completely different footing from other forces.
Yeah. So, the next question, it is often said that you have rewritten the general relativity, what Einstein did, and you took all the equations and you formulated, is it correct to say, quadratic equations out of them, those heavy, hefty equations, and you were inspired from the work of your friend Amitabh Sen. So, could you talk a bit about your work on general relativity?
Yeah, Einstein's theory is really supremely beautiful. I mean, it's sort of a lot of times, like Chandrasekhar used to compare it with Professor Chandrasekhar, who was a preeminent astrophysicist of last century. He often, I was very fortunate to have him as one of my mentors, and I'll tell you a little bit about that also, because those are important things for you, for the younger people to know. So he often compared general relativity with the best pieces of art, or music, and like Michelangelo's sculptures. I mean, in particular, he has a very beautiful quote that just like Michelangelo's sculptures are beautiful at no matter at what distance you look at them, and at every distance scale, new aspects of beauty are revealed. And that's literally true in general relativity. Those of us who work on it every day sort of see it, and in some sense, we expect this to be happening, and sometimes when it doesn't happen, we are very puzzled. And so almost always it's really beautiful, and it's beauty at different scales all the time. And it's really sort of a beautiful confluence of mathematics, very deep conceptual ideas, and physics. All this, philosophical conceptual ideas and physics, all those things. So this is this is what is a kind of great strength of general relativity. But it's also true that the way Einstein formulated his equations using space-time metric as a fundamental variable, so to say, they're complicated. They're among the most complicated equations in physics, right? In fundamental equations in physics. And that is why, in some sense, the progress in understanding the physical content of general relativity has been slow. I mean, Einstein discovered the theory in 1915, but I think it is fair to say that in the first 50 years, until about 1965 or so, there was, of course, progress, and a lot of important works were done. But the full content of the theory was not understood, and that is because equations. So first of all, I just want to tell you conceptually and scientifically what I did and what the new reformulation is about, and then tell you a little bit about anecdotal things about how it all happened. Actually, it goes back to the previous question that was asked about what is different between general relativity and rest of fundamental interactions. And I explained what the difference was, that this is really embedded in the very geometry of space-time. So I took the point of view that, well, let us look at how the other interactions are really described, mathematical variables in terms of which these other interactions are described. The mathematical variable there is really a vector field. Sometimes it's called a connection. It's a vector field which, for example, if you have electromagnetic field and you want to take an electron and charged particles to transport it from one point to the other point, then what you need is you need to know the vector potential of the electromagnetic field in order to write down the propagation equation. So this vector potential is, and the same thing happens to be true, surprisingly, for quantum. Those vector potentials are more complicated, they're matrix valued, so to say, but they're vector potentials. Whereas in general relativity, it is really the space-time metric. There's no vector potential fundamentally. So one of the motivations was that, well, can we perhaps, I mean, we're not changing the theory. That was an important point for me. We want to keep general relativity, but maybe formulate it in a different way. And if you formulate it in a different way, introducing some new concepts, then maybe new aspects of the theory would become more clear. And in particular, I wanted to formulate it from the point of view of the quantum theory, not so much classical theory, but quantum theory. And so the reformulation I found is really the fundamental variable is not a metric. If you like, metric is like an immersion concept, if you like. But the fundamental variable is analogous to the vector potentials. And what this vector potential enables you to do is to transport, to say how to propagate, how to move a object with a spin, like electron, or the fundamental spinners of the fundamental particles up here. In a gravitational field, a particle with a spin. And that transport is really is made by a certain vector potential. And so the idea was to look at this vector potential as a fundamental object and metric as a secondary object. And then surprisingly, so one is in a way doing two things at the same time. Once, on the one hand, one is casting the mathematics of general relativity in the language which is similar to that of other interactions, because all of the interactions are in terms of these vector potentials rather than metric. And so so metric measures distances between 2 points, for example, or how light propagates. That is what is determined by metric. Whereas, as I said, parallel transport, how you transport some elementary particles along a given path is dictated by these vector potentials. So the two a priori look quite different from each other. But if you have a metric, you get a parallel transport, and the point was that why not put it on its head and make the parallel transport or the vector potential as a fundamental object. And then what I found was, as you said, that in that case, if you know the basic mathematics of these vector potentials, which are metric valued and so on and so forth, and you say that, well, let's suppose there is no metric. See, all of the forces of nature, those theories are formulated in a given space-time. So there's a metric, that is the space-time geometry is given to you. But here you say, no, I don't have a space-time geometry. I'm trying to create space-time geometry. So can you write down some equations nonetheless for vector potentials without reference to space-time geometry at all, without using the idea about space-time geometry? And it turns out that there are very few things you can write down, right? Equations you can write down. If you just give yourself this as a principle. And the simplest equations you can write down, and as you say, they're kind of at most quadratic in the vector potential and quadratic in its canonical conjugate variables. So what is canonical conjugate? For a particle, if you've got a position of the particle, then the momentum is canonical conjugate. So if you have vector potential, then there is an electric field, which is canonical conjugate in other interactions, like the electric field that you are familiar with in Maxwell theory, in electricity and magnetism. So if you say that, well, I want to write down the equations, which are the simplest ones in terms of this vector potential and the conjugate electric field, but that's all I'm given. I'm not given a space-time metric. So there are very few equations you can write down, which are the nice invariance properties. And it turns out that those are precisely Einstein's equation. I mean, those turn out to be equivalent to Einstein's equation once you create a dictionary about how space-time metric is to emerge out of them. So what, if you like, is like going under and looking at the subject in a lopsided way, upside down way, and then somehow the structure simplifies. I don't want to say that this simplification means it does make it much easier to solve equations, but the concepts that come from the metric in general relativity are absolutely fundamental for classical physics. So I don't want to say that you can, metric is not important, we can just get rid of it. No, those concepts of classical physics are fundamental, very fundamental. But the suggestion is that for quantum physics, maybe metric, space-time metric should be thought of as an emergent or a derived quantity, and it is the fundamental objects in terms of which microscopic building blocks of space-time geometry are described should be these vector potentials.